Hi, my name is Tanvi and I'm a senior majoring in computer science. I'm a 2020-2021 Hume Scholar, and I've worked with Dr. Padraig Maloney, Wes Lawson, Michael Raker, Charles Ott, Erica Chu, Charles German, Shannon McLenathan, and Brett Parker from Leidos. Over the past 2 decades, use of the electromagnetic spectrum has increased significantly. More and more people have cell phones, laptops, tablets, and other devices that emit and receive signals. One of the biggest challenges that comes with this increase is managing who can use what bands of frequencies in both military operations and humanitarian situations. This is to make sure that no communications affect each other and either jam or disrupt each other. Normally, the use of certain bands of frequencies is highly planned out and optimized for maximum utilization. However, in case of an emergency, such as a natural disaster, there's really no time to extensively plan out what groups of people have access to what bands of frequency at what time. This often leads to very non-optimal allocation. For example, perhaps only Alice and Bob are allowed to use signals at a certain frequency, even though they're in a location for a very limited amount of time. Visualizing RF signals in augmented reality allows for better planning in situations like this. By seeing what signals will be present at what time and what their shapes are, it is clear when there will be overlaps that could lead to disruptions in communication. The current way that the electromagnetic spectrum is allocated is actually through spectrum auctions. Companies and other stakeholders bid to have access to blocks, which include a number of frequencies in a geographic region. For better allocation, 3D visualizations were necessary in order to understand when conflicts will arise. Visualization of RF signals in augmented reality, or AR, has also been done in different contexts. One example of this is an application called the Architecture of Radio that attempted to visualize RF signals in the vicinity of the user. This app compiled information from multiple public datasets to find signals that came from wireless routers, cell towers, and even satellites. However, this app was really more of an artistic experience than a tool to measure nearby RF signals, because all of the waves that were displayed were calculated from a user's distance to these routers, cell towers, and satellites. Beyond that, there have also been projects to display RF signals for educational purposes. In the 2018 paper by Christopher et al., the group visualized signals from objects such as dipole antennas and mobile phones. However, none of these existing approaches have aimed to visualize and really interact with signals to determine when there will be overlap. The aim of this project is to visualize RF signals in augmented reality, or AR. This allows for complex connections between multiple entities to be seen and interacted with. When a user interacts with an object, information about that object will also appear. To create all the shapes in AR, the Unity game engine was used. In addition to that, the mixed reality toolkit for Unity provided a lot of the basic building blocks for interaction components. Finally, all scripts for interaction and reading in data were written in C#, and the HoloLens emulator was used to actually view AR scenes. For this project, objects representing various signals were created based on input from a JSON file. The input information included a name, shape, color, frequency, and position for a signal. All of this information is displayed if an object is clicked on an information card. These objects can also be grabbed and moved around to demonstrate how possible conflicts could be fixed. This is an example of a sample scene that can be generated. 4 different signals are shown with different colors and shapes. The green spheres on the right show how signals may overlap, and colors indicate signals that are related to each other. Perhaps one is an emitter and the other a receiver. Although this is a fairly simple example, it demonstrates how multiple types of signals would look relative to each other. This video shows the same scene. Since this project uses the HoloLens in augmented reality, it is possible to move around the scene quite easily. As you can see, we can zoom out to get a broader view of the whole scene or zoom in to see certain objects. We can also pan around and get a better view of where objects are. Finally, we can interact with objects by clicking on them to display some information. All of these abilities give us a better way to understand signals and how they may interfere with one another. Work could be continued on this project in multiple directions. One really important addition would be to place objects in the real world rather than simply relative to each other as they are now. The current examples have been from a simulated dataset in order to ensure that various conditions would be met. However, displaying signals on top of real-world objects would give better insight. In addition to this, it is important to be able to view these signals over time, with users having the ability to fast forward, pause, and rewind. In cases of signal overlap, users will need to inspect further and possibly change bands of frequencies, for example. Finally, an important next step would be to make recommendations based on conflicts between signals. In the case that there was a conflict, various algorithms could be applied to determine what the best fix would be. Overall, augmented reality visualizations provide a good way in order to better understand and manage communication of complex RF signals. This work is really a starting point for these visualizations and demonstrates how different ideas with signals can be shown. This work wouldn't have been possible without the support of Colleen Bartos and the entire Leidos team. Thank you for all of your help and support.